circuits, the first thing you actually need to know is the atom, how to draw it, what it's made of, what are the subatomic particles that makes up the atom, a little bit about all three of those particles as well. And you'll be expected to draw the atom with the correct number of protons, neutrons, and electrons as well, orbiting the nucleus in their shells. Alright, so first of all you have the three, proton, electron, neutron. We should know from before in chapter 6, radioactivity, that the proton has mass, relative mass of 1, neutron, relative mass of 1 also, and then the electron has a relative mass of a negligible size, so we just say 0 for GCSE. Charges, we've got proton plus 1, neutron obviously neutral, so 0, and the electron is minus 1 as it's negative. If you were asked, for example, to draw the atom of oxygen 16-8, we should know that the 16, the mass number, which is protons and neutrons, also known as nucleons sometimes, then that would be 16. The atomic number, which is 8, in this case tells you the proton number, but for atoms we know that that is also the electron number, because the number of protons in an atom is exactly the same as the number of electrons if the atom is neutral, because the positives balance the negatives and you get an overall neutral charge. So if there's 8 protons according to the atomic number, there must be 8 electrons as well. So to draw this atom of oxygen 16-8, you need a nucleus which goes at the center. You have to draw individual particles, protons and neutrons. So you have to identify that there are 16 particles inside that nucleus, 8 of which are protons, which I've shaded so you can see them coloured in, and then the other 8 which are not coloured in, they're your neutrons, and they're all in that nucleus in the centre. You have to show the individual particles. You can't just draw a nucleus and write A, P, A, N. Alright, you need to be able to draw those if the examiner asks. And then the electron shells, of course, we said already there are 8 electrons to balance the 8 protons, but in the shells, the first shell has 2 electrons, and then every shell outside of that, as far as we're concerned for GCSE, you have 8 electrons to fill a shell. But because we have 8 in total, and there's 2 on the first shell, then there's only 6 on that second shell. So 2 there, and then 6 around the second one to make your total 8 electrons. They could ask you any element from the periodic table. They'll give you the mass number, the atomic number, which means you can figure out the electron number, and then you draw that atom exactly the same way as they have here. The reason that they're making you do this on the atom in electricity right at the start, because you have to understand electricity, which we'll learn as we go through, is a flow of electrons, a flow of charge. Now, which materials do we use all the time for electricity and transporting electricity around circuits? Is metal, copper most commonly, and the reason metals are the best conductors, so they allow electricity to flow through, they're a conductor. The reason they're the best conductors is because they have outer shells. This is a poor example, obviously this is not a conductor, but they have shells on the outside which have what we call delocalized electrons, which is 1 electron on average on each atom that is available to move between the atoms within the material. So they're not fixed to the atom itself, which means if we have a voltage, then we can provide that current and the electrons will flow around the circuit. So that's why metals are the best conductors of electricity, because of their electronic structure. So you need to be able to draw that and explain that the reason metals are such good conductors of electricity is because their outer shells have these valence electrons, these delocalized electrons, available to transport the electrical energy around the circuit. The next thing you need to be able to do, recall the diagrams and the names of as many different circuit symbols as you could be asked for the GCSE. So you have a cell, a battery. If you've got the notes on this slide, you'll see them all anyway. A battery, as you'll notice, is 2 cells. So a cell is not a battery. If you have just the one cell with a small and large line, then it's not a battery. But if you put 2 of those cells together, then you get a battery, and so on and so forth. So a battery is 2 or more cells joined together. Resistor, bulb, switch, voltmeter, ammeter. You need to be able to draw them all, state what they are, but also you need to understand a little bit about what they do. So the cell and the battery, that's your power supply for the circuit. There's your negative is the small line, and positive is the long line. And this essentially is a difference in charge, positive, negative. We'll learn in the next section that it's potential difference is what it's called, voltage, potential difference. And what that means is you have a difference in charge, positive, negative, and we know that opposite charges attract. So without that, the electrons throughout that copper wire in the metal, they're not going to flow around the circuit if they're not attracted to an opposite charge. So your cell battery, that is providing your energy, the power that your electrons need to be transferred around the circuit. Resistor, it resists the flow of current, so it slows down the flow of electric current. A bulb, what essentially a bulb does, a filament bulb for example, it transfers the electrons into a very small metal wire. That then causes a lot of friction in the filament. There's a lot of collisions between the electrons themselves and the protons, and then that generates heat, as we know. And the more and more heat that we actually get, so the more heat that's generated in this, the higher the temperature, the shorter the wavelength of emitted radiation, chapter 5. So the higher and higher this temperature of this filament gets, eventually it's going to stop producing just thermal energy, but the temperature is going to be so high that the wavelength of radiation emitted will be visible light as well. So a filament essentially works by using thermal energy, but it gets so hot, the temperature gets so high, that it can actually emit visible light as well. Alright, so that's a filament bulb switch. Opens and closes the circuit. If you open a circuit, there's no attraction to the positive. The electrons in the material can no longer feel that attraction. The potential difference is gone, so you get no current flowing through the circuit. Voltmeter measures the voltage. Ammeter measures the current, and the reason it's called an ammeter is because the current is measured in amperes, so it's the unit of current. Variable resistor, you can change the resistance using a device. So you select the resistance. This one is a fixed resistor. So this has a fixed resistance. Once it's in the circuit, it doesn't really change. This one you can select whatever resistance you want. A thermistor is a thermal resistor. So the resistance of this component will change depending on the outside temperature. Alright, we'll look more in more detail at that soon. An LDR is a resistor, it stands for light dependent resistor. So the resistance of this, which you can see is the same as the fixed resistor, in a circle with arrows going in. These arrows going in represent light coming in. The resistance of this component depends on the light intensity around the outside of the circuit. Two more, you have a diode. The diode looks like a play button with a line in there. It only allows current to go in one direction. We'll find out why that's important in the future of this chapter. And then again, an LED, which is a light emitting diode. So essentially, the arrows again are showing you that it is emitting light. The fact that it's a diode just suggests that if current goes one way, nothing will flow through, so there'll be no light produced. But if you change the direction of the current and the current passes through, then light will be emitted. And they're the circuit symbols and components that you need to be aware of. Draw them, name them, and give a little description if required, what they do, how they work. Moving on to conventional and electric current. Two types of current, essentially, that we still use, we still describe, only one of which is technically true and correct. So conventional current is a very, very old way of thinking about electricity. So if you'll see in conventional current, we go from positive round the circuit to the negative. So we're saying essentially that current is flowing positive to negative in a circuit. Now that's not the way that we see electric current anymore. It's the conventional way of thinking about current. It was invented essentially by Benjamin Franklin. They didn't yet know the structure of the atom entirely. They didn't know that the electrons on the outer shells of the metal were the ones that were taking the electricity through. So they just assumed conventionally, hence the name, that conventional current went positive to negative. Okay? We now know the structure of the atom. We know why metals are such good conductors of electricity. So we know actually that the electrical current is transferred around the circuit by the negative electrons. So electrical current is what we know is true today, that negative to positive, whereas conventional current is the way they used to think, is that it went positive to negative. Two more things in 10a, which is series circuit and parallel circuit. A series circuit, as you can see, is one series loop of components. You only have one loop in a series circuit with components all the way around the circuit. So, looking at this one, we have a cell, two bulbs. if this cell has 3 volts, these bulbs are in series. Voltage in series is shared between the components in the circuit. So for example, 3 volts on the cell there, 2 identical bulbs, which is very important, get 1.5 volts and 1.5 volts each. So voltage is shared between components. Now, I'm going to skip step 2 just quickly. This voltage is shared 50-50, so 1.5, 1.5, because the resistance of these 2 components is identical. So the voltage shared in a series circuit depends specifically on the resistance of each component. If they're identical components, they get exactly the same share from the supply. However, if you have a component, for example, let's say this one has a higher resistance than this one, then a higher resistance component will take more of the voltage. So higher resistance component in series takes more of the supply. Okay? If this was twice the resistance of this, then it would take twice the voltage from the supply. For example, it would take 2 volts, this would take 1 volt. Why is that? Why does the higher resistance component take more of the supply? This rule number 2, current is the same everywhere in a series circuit. It is the same loop, it's the same circuit, it's made from all the same electrons, so the current must be the same everywhere. Now, if you have the same current going in and out of this bulb as you do going in and out of this bulb, and yet they have different resistances, that means it's harder for the current to pass through the one with a higher resistance. If it's harder for current to pass, yet the current through both is the same, then the one that the current is passing through, which is harder, must get a greater push. It must get more energy from the supply in order to transfer the same current through both components. So I'll say that again. In a series circuit, current is the same everywhere. That means going in and out is the same current at the same time, no matter what the component is. But if one component has a higher resistance than another, then it's harder for the current to flow through that resistor. In order to maintain that constant flow of current, you have to push the current through the higher resistance more. In order to do that, you will take more of the share from the supply, and obviously the lower resistance will take less. So a greater push through the high resistance means more voltage from the supply, and a smaller push through the lower resistance takes less supply. Again, if they're identical components, then you get exactly the same share as the voltage. So 3 goes to 1.5, 1.5, and the current would be exactly the same everywhere. Slightly different rules, almost opposite rules in parallel circuits. So as you can see, in a parallel circuit, at first glance, it has 2 parallel sections. We call those sections branches. So each branch on a parallel circuit has a certain set of rules, and they'll get a certain voltage and certain current. If again the supply cell is 3 volts, 2 bulbs in parallel, they're identical bulbs again. However, this time, this branch and this branch have their own electrons in their wire. They have their own branch of electrons. So they take exactly the same share, not even share, they take the same maximum supply voltage. So if the supply voltage in a parallel is 3 volts, every single branch in the parallel circuit takes that supply voltage. 3, 3, 3. You can have 100 bulbs in parallel, each getting 3 volts from the supply. What you don't do in a parallel is add the voltages of each branch to go back to the supply. It doesn't work like that. If the supply is 10, each branch gets 10. Okay? However, current is slightly different. Current in a parallel, you've got 2 amperes here. At this point, all the way around here, you have the total current in this circuit, which for this one is 2 amperes. But in a parallel circuit, current splits at a junction. So if this is the junction here, current comes in from the negative terminal to the branch junction here. Again, both bulbs are identical, so the current splits 50-50. So the ratio is literally the same for both. So you've got 1 ampere goes down this branch, 1 ampere goes down this branch. Alright? The same thing happens again if you have different components with different resistances. So the only reason it's split 50-50 is because they're identical components, they have the same resistance. But if one had a higher resistance, let's say for example the one on the top branch has a higher resistance, then it's going to be harder for the electrons to flow. Now why would more electrons flow through a wire that is harder to travel through when it's a lot easier to go through a path with lower resistance? So in this case, higher resistance on a branch receives lower current through that branch. So current splits at the junction. If the resistance on one branch is greater, the current through that branch is lower. So it's kind of the opposite of voltage, because higher the resistance in a series, which is here, higher the resistance, more of the supplied voltage it gets in the share, but higher the resistance on parallel, less current passes through that branch, because it's harder to travel through. Alright? So each branch receives maximum supply. Current splits at a junction, however, the amount of current depends on resistance, and the higher resistance receives a lower current.